this is our diagram of the CPU, okay? Now, when you go up to A level, you'll need to know about the different registers that are also inside the CPU, okay? Now, if I draw another diagram of the CPU here and my RAM, so this is my main memory, okay? So this is my RAM, okay? And inside the CPU, believe it or not, please do not write these registers in your spec. It's not in the AQA spec, all right? But there are different registers, okay? For example, there is a register called the program counter, okay? Now that program counter is like a number, and it keeps track of where the program's at. So it'll be like 1, 2, whatever line of code we're on, okay? That is then copied into another register called the memory address register. Alright, so this is what's happening as part of the fetch to code execute cycle. So you've got a memory address register. Now inside your RAM, you've got lots and lots of instructions. That's why all the programs you are using on the computer, such as your Word, your PowerPoint, your Excel, any of the games that you play, they've got all these instructions inside the RAM. Okay, that RAM, okay, might have load. I don't know, memory 101. It might have add 302. There's lots of just instructions and data, okay? Now what the computer's got to do on every clock pulse is it's going, the program counter that keeps track might be 1, 2, 3, 4. So what happens is that instruction goes into the MAR. So it says on line 1, okay? Then the memory address register will go to position 1, 2, 3, 4, 5, 6 and retrieve that instruction, alright, and get that and trace it into the MDR or MBR, alright? You'll learn more about this at A level, but what's happening every time the clock ticks on the computer, a signal is sent to the control unit, okay, which then the control unit will say that it needs to start the fetch to code execute cycle. Am I making sense there? But these are the things that you're not talking about in your exam question. You're not saying, so this is what happens on one tick, all right? So we go to the PC, goes to the MAR goes to that address, gets that instruction, and then the result will be stored in the accumulator, okay? So that might be like the result of all of that is like 1, 2, 3, 4, and so on. But what happens is we have a system clock, all right? That clock is sending regular instructions to the control unit, all right? So there is a signal. The thing that lots of people keep forgetting to mention when they are talking about the control unit and the clock and the system clock is that that clock has a regular signal. So if you want to make a note of this, it has a regular signal and pulse. That is a key term that people keep forgetting when they're talking about the clock. So can you please, as a matter of urgency, write that down. So the system clock has a regular signal or pulse. Now I want you to think about it. Think about what clocks do in music. 1, 2, 3, 4. So obviously if you've got a clock on the computer, that's obviously running at whatever clock speed. What does a metronome do? Synchronizes everybody and helps keep them in time. So what do you think the clock does? It synchronizes everything, okay? That word, all right, when we're talking about the clock, a lot of people do not acknowledge that it synchronizes all the components. I'm sorry if you can't see this in the green pen, all right, but I've written there, synchronizes the components, okay? The one last thing that you could potentially talk about, if everything is based on the clock, right? So that's like fetch 1, fetch 2, fetch 3, fetch 4, fetch 5, fetch 6. You understand what I'm getting at, yeah? And that's synchronizing everything so that the PC, the monitor knows when it's getting the next instruction. I can visualize it, all right? One last thing to mention about the clock. Where am I going with that? Why did I just speed up the tapping? All right. So it influences the number of instructions carried out in that time, because everybody in the next question in the exam got this: the faster the clock speed, the more instructions. But you didn't actually write that in the previous question. So you acknowledge what the clock is, acknowledge that there is a pulse, acknowledge that it synchronizes all of this and keeps it all running on time, but then you say the impact. So the impact is the faster, the more instructions, okay? Sorry, I can't fit that on there, all right? So we've acknowledged what the clock does, but the clock's job is to kind of keep it all in sync. But what did I say the control unit did a minute ago? Doesn't fetch, all right? The control unit's job was to kind of go, like, send that signal and say, okay, I'm about to start the fetch the code execute cycle, okay? Yes, it decodes, but what that is that coordinates it and say, okay, start the fetch cycle. So the control unit, I'm just going to write this down here, or I wonder if I can fit it up here. Let's put it up here. The control unit, I'm going to underline the key words you need to be thinking of, all right? First of all, it does decode, all right? So you can get that down. So it does decode the instructions. Then, what you've got to make sure, what's it doing? It's sending control signals to other components. When you're talking about the CPU, it's really important that you acknowledge the word signal. Notice I had to talk about the signal for the clock and talk about a signal from the control unit as well. That is one word that I'm missing a lot of in the theory paper, I'm afraid. There's one last thing that the control unit does. How does the control, think about it, how does that control unit know that something's happened? Yes. Where does it get those signal from? How do you interact with your computer? Your inputs and outputs, your other components. If I think about it, if you were in an engineering workshop, all right, they're all computers, they've all got on and off switches, and something happened on one of those machines and you needed to stop it, you need to interrupt it. Well, the control unit needs to know that that interrupt happened. So if you press like stop on the keyboard, it stops because it's received that interaction, that signal from an input device. So it interacts and coordinates I/O devices as well. Okay? So think about it. The control unit needs to have something that tells it, oh, I need to start this. Like when you press the save button, as soon as you press save, the CPU now needs to start processing and saving all of those instructions. But it doesn't know to do that unless it's had that signal from an input device. Think about it. Hopefully, but this is all it's all the extra stuff around your answers. You all know it. It's just all the extra stuff that kind of builds up your answers, just kind of missing at the moment and needs a little bit more finesse, all right? Let's go on to the cache. The cache I was pretty happy with. Most of you seem to understand that it's there. So here's my RAM, right? What do you think might be a regular instruction that I'm going to have to run all the time in the RAM? Okay, I'm going to help you out with this. Imagine I've got a program right here that needs, every time it's executed a loop of code, it needs to save it. Okay? Well, that save instruction, we're going to say in register 303, that save instruction, because it's going to run at the end of every loop, I might go, okay, well, I don't want to keep getting that from the RAM, so I'm going to store it in the cache. That now means that that instruction, it doesn't need to go all the way to the RAM, to that, process it again to get the output. The control unit can just keep going to the cache now. Which is closer? Which is closer? Cache, okay? So what's happening here, all right? Yes, it does improve efficiency. And speed of retrieving data. Notice there, okay? Notice there, I've not stopped at efficiency. That is a common exam error. People saying, it makes things more efficient. How? I need to know. How? The so what factor. Because, alright? So, improves efficiency and speed of retrieving data. That's what it means by efficiency, the speed it's retrieving data. And then you can say, because it does not have to go to the RAM all the time. Alright? So, it doesn't have to revisit the RAM regularly. But then you can say, what's the one bit I haven't mentioned yet? This is the one that you got the mark on. Yep. No, I've just said that because it doesn't have to revisit the RAM regularly. Alright, you could say cache is closer and stores, no, you didn't say this bit, and stores regularly used in instructions. The difference between the different three things that I've just written there is about the regular used instructions. Alright, you could give an example such as save that you need to do, however you want to do it. I'm hoping that that diagram's kind of helped you think about it. There's one component that I haven't mentioned that could come up in an exam. It didn't come up in your exam question. Something else that I need to work with there. Yeah, the ALU. The job here, alright, so imagine the control unit has sent the signals, retrieved the data, passed the data into the registers, and the registers have got to interact with the ALU. The ALU's job, alright, and if you want to, if it helps you with revising, because some of you are more visual, why don't you draw your logic gates on there. Sorry, that's a NOT gate. Alright? That's where all your logic is happening. All your logic gates and logical comparisons. So many times, you haven't had this yet, but I don't want to put any bets on it. People, when they're talking about the CPU, might write in there that what does the ALU do? The arithmetic and logic. You're not getting any marks for that. You're stating an acronym. Okay? What you are getting the mark for is logical comparisons of data. Mathematical operations such as add, div. Do you see what I'm getting at? So you write on there add, div. Alright? So just to make a little note here, logical operations / comparisons, and then mathematical, how do I spell mathematical? Mathematical operations such as add, multiply, and so on. Alright? In fact, don't put multiply. Computers actually can't multiply, believe it or not. What do they use? It's a logical operation that computers do. Somebody just said it. A binary shift, okay? It's a misconception, but when you use the multiply operator on a computer, what it's actually doing is it's doing a binary shift left or right. Yeah? So that, again, so that's, so hopefully that summary today gives you a bit of help on the CPU. You are now free to go over those questions.